Take a look at section 3.4. And this is a rather lengthy section. Don't y'all love it when I tell you in advance it's going to take forever? Okay. Okay, the derivative as a rate of change. Okay, the derivative as a rate of change. Now, before we jump into this, the questions that are given that sound easy are kind of hard, and the questions that are given that sound like they should be hard are actually kind of easy. So you're going to get a real mixture of emotions, I guess, as you work the homework in this section. So I need to do a little bit of a review and really do a little bit of clarifying some terminology in here that will make your life much happier. So when you're doing your homework, don't get too frustrated. Be certain you understand the question before you try to answer it. Okay, very importantly, we have the average rate of change. Okay, the average rate of change. And really what the average rate of change is it's really the slope of a secant line. Okay? And we want that secant line to be as close to being actually the same as the tangent line as possible. But really, it's only the slope of the secant line. So really, it's a rough estimate, but we try to make it good. It's a rough estimate of the slope of the true tangent line. Rough estimate of the slope of the true tangent line at a point. So in other words, try not to or don't equate the average rate of change with the value of the first derivative, because it's a rough estimate. It's not as exact. It's not the limit as the 2 points approach each other or they combine with the h value of 0. So when they're asking you for the average rate of change, be careful that you come in here and you calculate this using strictly the slope formula. That is the average rate of change. Okay, using the slope formula. It is that simple. So you don't even really have to jump so far into understanding your calculus knowledge now. It's really a very basic understanding, and you're just going to use the slope formula. Now, where this progressed, and which is where it's really progressing in this section, is into what we refer to as the instantaneous rate of change. And I'm going to read what this author, Mr. Thomas, has to say to us. And he says, if we interpret the difference quotient, f of x plus h minus f of x over h, as the average rate of change in f over the interval between x and x plus h, we can interpret its limit as h approaches 0 as the rate of change at a point, instantaneously. So when we're doing the limit as h is approaching 0, or the distance between our 2 points, which are creating our secant line, when we finally make it into a limit, getting it exact, then we become the instantaneous rate of change. Instantaneous rate of change. So the instantaneous rate of change is the change very selectively at an exact point on the line, and this is where we come into the first derivative. This is when we took the limit of the difference quotient as h approached 0, limit, which we now also know how to use the shortcut differentiation rules to calculate. Okay, that is the instantaneous rate of change. And really, we normally come in here now and we use our differentiation rules. To calculate that. So we don't going to go through the whole limit thing. We're going to just use our differentiation rules to make that happen. Now, let's see if we can kind of get a better understanding of what is the difference in the average rate of change and an instantaneous rate of change. I mean, you algebraically can see it now. One is just a slope formula, and one is truly that limit, which is our first derivative. Now, the way I kind of look at this to try to explain it, the difference in the two informally, is I often think of myself as I drive my children to Arkansas. I have 4 children, and all of my sisters and my parents all live in Arkansas. And so when it's time for me to take these kids and go visit all the family, I usually drive through the night. So the distance I usually travel is about 500 miles. And I have 2 options. Okay, I can either drive during the daylight hours when I'm not so tired, okay? And when I do this, and I'm driving up Highway 59, okay, my speed, okay, or my velocity usually runs, or I set that cruise control on about 70 miles per hour, okay? And I have to go through all a million little towns, and I have to slow down and go through lights, you know, and then the kids have to stop and go to the bathroom. We have to stop at McDonald's and play for a little while and stretch, all these awful things, okay? And so by the time I get there, it takes about 9 hours, okay? That's the pits. We're all grumpy, you know, and it's almost dark, and they're wired, and I'm tired, the whole 9 yards. Okay, so what would be my average rate of speed? What would be my average rate of speed? Well, what did I do? I went 70 miles per hour, right, in 9 hours, or actually, let's take this back. I went 500 miles in 9 hours. So what was my average rate of speed? What y'all come up with? 55, approximately 55. That's pretty lousy, right? I'm setting that cruise control on 70. I've got that cruise set, but I'm only really making this average rate of speed because I'm going through little towns and I'm stopping at lights and the kids are making me pull off and all these lovely interruptions. So this is my average rate of speed. But when I'm on a straight stretch with 4 lanes and there's no cops around, what is my instantaneous rate of speed? Okay. Instantaneous rate of speed is changing through the entire trip, okay? Okay. Okay. A lot of the time I'm going at 70 miles per hour. But then there are other times where I'm having to slow it down and I'm only going 45 while I'm going through these small towns. There are other times where my instantaneous rate of speed is 0 because I had to stop. Do you see that? So do you see the difference in the instantaneous versus the average? Instantaneous is a moment in time. And there's times where I'm making good time, and then there's other moments where I'm not even moving. And that's what your instantaneous rate of time is all about, so that you can see the difference in these two in order to understand when they ask you the average rate of change versus the instantaneous rate of change, you have a much better perspective on it. Now, there's some more terminology in here. I mean, you got to get this right, or you'll never get these answers to these questions right. Okay. Okay. So now here's some terminology. And you know, they don't really go into any great depth of explaining this to you. They just assume you know what you're doing. If you're like me, you don't. Okay, you have to kind of look at this in depth. Okay. All right. You have what is referred to as distance, and also what is referred to as displacement. Okay, you have distance and you have displacement. Displacement is very straightforward. It's like taking a picture of where you start and where you stop and just calculating the distance in the two. So your displacement is literally the difference, so how do I say this? The distance from end point to initial point, or to original point, to original point. So where you ended to where you began. How far you went from the moment you took off till the thing stopped. Okay. Now, that displacement doesn't necessarily have to be the same thing as distance. And here's why. If you are in a car and you start at this point, and, you know, I take the kids to school, then I drive back home, and then I go to the bank. which is the other direction, and I drive back home, okay? And then I go, I don't know, to the grocery store, and they say, how far is she from home? Displacement is how, at that point when I stop, displacement is the distance from my home to the grocery store. But the distance I traveled was this, plus this, plus this, plus this. You see the difference? Okay? So distance is the total distance I traveled, not where I started and where I stopped, but everything I did in between. Okay, so this is truly all distance covered, all ground covered. How's that? It's not just from the beginning to the end, but it's everything that happened in between. All right, then we have velocity and we have speed. Okay, now velocity is usually v of t, okay, like this. Velocity based on the amount of time you're driving or whatever object is moving, whatever. Velocity can actually be positive or it can be negative, okay? So velocity can be positive, which normally means to the right or up, okay? And velocity can be negative when you're going backwards or backtracking, okay? Backwards or backtracking, okay? So my velocity was forward when I took the child to school was positive, but my velocity would be negative as I returned back home. And then velocity would be negative when I went to the bank, because that's still backwards. And then velocity would be positive when I returned back home, and positive to the grocery store. So it's the direction you're traveling, more or less, is going to tell you whether your velocity is positive or negative. Speed is the absolute value of velocity. So if I'm going back home or I'm going the opposite direction from home to the bank, I'm going maybe what you would say a negative 50 miles per hour velocity. But my speed is just 50 miles per hour. See the difference? So velocity incorporates direction. Speed doesn't care. How fast am I going? Okay. So get those two straight. Then you have acceleration. Acceleration is your change in speed. Okay? Like I'm on cruise control, but somebody is going really slow in front of me, so I come off of cruise control to go around them. I'm speeding up. Or I can't go around them because there's a big old truck coming up my left side, okay? And I have to brake off of my standard velocity, okay? So your acceleration is also going to change. Your acceleration is your change in velocity. Okay, now, here's some variables that they're using. When they talk about distance or even displacement, they use s or s of t. Actually, they also use f of t. They interchange all this. S is common, and then for some reason they'll change it to f of t. That means just, they just do kind of what they want, okay? So I seldom go to f of t. I usually call it s of t when I throw it into function notation. Velocity, v of t, is the first derivative of your position function, or the first derivative of s of t. It's the first derivative. And it can be positive or negative. So that's velocity. And when you take the absolute value of it, it becomes speed. Acceleration, a or a sub t, is actually the first derivative of velocity, but the first derivative of velocity is the second derivative of your position function. Okay, so you have your position function, your first derivative is velocity, and your second derivative is acceleration. Then there's one more thing that we really seldom talk about, and it's called jerk. It's called jerk, and they talk about this in the textbook. How did they talk about it? Jerk. A sudden change in acceleration is called a jerk. when a ride in a car or a bus is jerky, it is not that the accelerations involved are necessarily large, but that the change in acceleration is abrupt. I think that's very well written. So the change in the acceleration is abrupt, which is a jerk. And so, you know, I don't even know, we've never even used a variable for this, and they don't, oh, they do use J. Okay, so this way, and we really seldom do this. An impulse, that's kind of a neat way of looking at it too. So jerk is the first derivative of acceleration, which would actually be the third derivative of your position function. Okay, so kind of get it, you got to get all that straight. You have your position function, your velocity is your first derivative, your acceleration is your second derivative, and jerk, if you ever really aren't going to see that, is your third derivative. All right, and try to keep the definitions in your head clear. The difference in distance and displacement, velocity and speed. Velocity and speed seem like they should be the same. Speed, but velocity, remember, can take a sign, meaning it can be negative or it can be positive. Now, this gets really interesting when I show you a graph. I'm going to try to give you a graph nice and clean and neat. And again, the reason this section is going to go kind of slowly is I'm trying hard to get the concept across before we really go into the questions, which will make answering the questions hopefully much easier. Okay, negative and positive velocity. All right, here comes a graph. I'm going to have to get me a ruler at some point. My son had it this morning in the living room. I was wondering where the thing was. My good one. And I forgot to take it from him. And then the little stinker, I gave him a box of chocolates for Valentine's Day. And as we were leaving, he said, "Can I take this to school with me?" I said, "Sure." And then after I got on the bus, I thought, you watch, he's going to give that to some girl. Right? That's right. I gave him 2 boxes of chocolates, so I won't be too upset with him. All right, so at 1, let's go to a height of 3. At 2, let's be at a height of 3. Oh, you are too bad. Bad boys. He's my oldest. He's 13. Okay, here's your graph. See if you can duplicate it. You're going to have a line like this, this. Let this one kind of slope down. And then that. There it is. My girls just opened it and started eating it for breakfast. Actually, I told them it was okay. Actually, my second son also, he did too. My oldest son was the only one who took it to school. Okay, take a look at this vertical value. This is velocity, and this is time. So this is velocity, not distance. This is like how fast the car is going, miles per hour kind of thing. Okay, how fast. Your vertical values are how fast. And direction, because we have some negative stuff down here. So when you're below the x-axis, you're having negative velocity. So let's just make a quick table over here of what's in this graph. The slope of the line. Okay, so at time 0, the velocity is this point 0, the vertical height. At, say, time point 5, halfway, let's say the height is what, 1.5? At time, say 1 second, the velocity is 3. Maybe it's 3 feet per second kind of thing. At time 1.5, the velocity is still 3. At time 2, the velocity is still 3. Then at time 2.5, the velocity is, say, half a foot per second kind of movement or change. Then at 3, your velocity is 0. What does that mean when your velocity is 0? You stopped at McDonald's. Okay. Then at 3.5 seconds, I'm going to say my velocity is about a -3. At 4, my velocity is at -4. At 4.5, my velocity, again, I'm going to say is a -3. And then at 5, my velocity is 0. So I stopped again. Oh, that's not a good thought. Okay. At 5.5 seconds, I'm still sitting still. The object is not moving. At 6 seconds, I'm sitting still, but I'm getting ready to take off again, right? It's getting ready to go. Then at 6.5 seconds, my velocity is like 1 foot per second. And then at 7, my velocity is back up at 2. Okay. All right, so let's think about this. We're sitting still. Then we go up to a speed of about 1.5 feet or whatever per second. Then we get up at 3 feet per second. And right in all this time period, we're holding steady. We're moving forward at a constant rate of speed, right? So forward at a constant rate of 3 feet per second, or whatever you want it to be. Then I drop it down to 1.5 or to 0.5 foot per second, so I'm kind of slowing down, right? My speed is coming down to the point that I stop. So I slow down, I slow, and I stop. Okay, then I take off again, but I'm going the opposite direction, right? I'm going kind of backwards, backtracking. So here I take off again, but I'm going backwards right here, and I'm still going backwards. All of this is going backwards until I get back till I stop again. So I go backwards at like 3 feet per second, then 4 feet per second, and then back to 3 feet per second, and then I stop. Then I stay stopped for a while. Then I take off again, and here I'm going forward again. And I'm increasing speed, right? I'm not going constant forward, I'm going forward and I'm increasing in my speed. Now, let's take a look at what is speed. Speed is almost the same as velocity, but it has no direction. So when speed is 0, I'm sitting still at time 0. Speed is 1.5. All this forward direction is great. Stop. And then right here, when I'm going backwards at 3 feet per second, speed is not negative. Speed is positive. And this speed is positive 4, which means my speed is increasing, though my velocity is decreasing. -3 to -4 is decreasing in number, right? Numerically, that's a decrease in velocity. So remember, velocity is a very numerical representation. So the negative tells you you're going backwards. And when you go from -3 to -4, that says velocity is decreasing, though speed is increasing. Do you see that? Velocity is decreasing, more numerically negative, whereas your speed was increasing. Okay, then you got a +3. Then you have a 0, you stopped, you stopped, you stopped. Your speed is always positive. So that's where it gets interesting. This is where the speed gets interesting, is when you go from -3 to -4, that means that velocity is decreasing, though your speed is increasing. That's kind of weird. Okay, that's kind of weird. Well, you're not really in reverse, okay? You're just going the other direction faster, but it's considered more negative because of the direction. So that's weird, okay? That's hard for me to even grasp. You just have to look at it numerically. When velocity is going from the -3 to -4, that number is getting smaller. So velocity is considered decreasing, though really the speed is increasing. So that's kind of weird. Now, the other thing that we need to briefly discuss, and you'll get, when you get into physics, this will probably become a little more important to you, is acceleration. Now, remember what acceleration is. Acceleration is the derivative of velocity. So acceleration is the slope of the tangent line to velocity. So it's the slope of this velocity graph. Okay, it's the slope of this velocity graph. So we're going to do some guessing here. Okay, so we're going to kind of go with the same thing where here is time at 0.51, and then we're going to see what in the world are we going to guess the acceleration to be, which is what are we going to guess the slope of this graph up here. Okay, so say the slope between 0 and 0.5, I'm going to guess that's about a 1. And it's between the two numbers. It's the slope. It's the difference of two numbers. So the slope here is about 1. Between 0.5 and 1 is about 1. Between 1 and 2, 1 to 1.5 to 2, in this region, it's a slope of 0, right? This is a horizontal line. It has a slope of 0. Okay, a horizontal line has a slope of 0. Think of the slope of the line. Okay, between 2 and 2.5, well, I don't have any clue what that is, but it's going. This is what your tangent line looks. I don't know, something like this. Okay, there it is. That's a negative slope line, right? So it's negative. So between 2 and 3 and all the way to 4. In all of this region, it's negative. Okay, in all of this region, it's negative. That's weird. Okay, and then when you go from 4 to 4.5 to 5, is the slope of the tangent line negative or positive? Over here, it's a positive tangent line slope. Positive slope of the tangent line. See if I can say that better. And hey, we're missing something really important. Right here, what is it? 0. Okay, so at 4, it's 0. It's negative between really 2 and 4, and at 4 it becomes 0. Then between 4 and 5, it's positive slope of the tangent line. Then between 5 and 6, what is the slope of the tangent line? What's the slope? Oh, 0. And then between 6 and 7, it looks like it's a slope of 1 this whole time again, positive 1. Okay? So that's kind of weird. So your acceleration is positive. My graph going on here. My acceleration is a positive 1. Then my acceleration is 0 because I'm holding steady. I am sitting on cruise control and I am not touching the brakes or the gas pedal. Then my acceleration becomes negative. And really right here it might be 0. It depends on the graph. You have to look at your graph as to whether it really flattens out there. And then it becomes negative until it hits 0. Then it becomes positive as you're going up the line. Then it's the acceleration, which is the slope of this horizontal line, is 0. And then it's a positive value again. So there is acceleration. Kind of weird, huh? So that gives you a little bit of a representation of acceleration. And then they talk about acceleration in your book. Also, here's a definition. Look at this lovely notation. Oh my. There's all that stuff I wrote about jerk. Okay. Acceleration is the derivative of velocity with respect to time. If a body's position at time t is s, which they're replacing with f of t, then acceleration will be the second derivative of the position function. and then jerk will be the third derivative of it. So there that is. So if you want to take a look at that, it is on page 127. I don't know how excited you are going to be about really looking at that, but if you want to take a look at acceleration and how they define it as being the second derivative, its definition is on page 127 of your textbook. Okay. So then what's going to happen is when you get into your homework, you'll have a question like this one. Something like this. They'll give you a graph, and they'll say, when does the body reverse directions, and when is the body moving at a constant speed? Okay. You can't reverse direction until you stop, right? So you're going to move for a little while, and then you got to stop to turn it around and go the other way. So think of a change in direction or a reverse in direction occurring when you stop, which means a change in direction occurs when your velocity is 0, right? Okay, so you got to look at this. This is velocity right here, your vertical. So when your vertical is 0, you're stopping. So it's 0 when you start. Of course, you're stopped before you start. Then it's 0 right here at 2 seconds. And then it's 0 at 7 seconds. That's where you stopped. Okay? So, come here, pencil. So right here you stop, and here you stop. Well, to change directions means your velocity has to either go from positive to negative or negative to positive. So the sign on velocity tells you when you change directions. Well, your velocity is positive here above the x-axis and negative here below the x-axis. So your velocity is going from positive to negative, so at 2 seconds you changed direction. Here you stopped. You were in the negative velocity zone, you stopped, and you went to the positive velocity zone. So at 7 seconds, you stopped and you changed directions. Now, if you were to do something like this, if I continue this graph, here your velocity is positive because you're above the x-axis, a positive 3, a positive 2, a positive 1, and 0. And then it's a positive 1, a positive 2, a positive 3 still. So here your velocity is positive, then you stop, and your velocity remains positive, meaning no change in direction. Okay, so the sign on velocity means if you're above the x-axis or below it. Acceleration is the slope of the velocity line. So if that's difficult to follow, I know you can follow it with the table. And if you have to make yourself a table just like that, and y'all can do it really quickly, then that will definitely make it so you can answer those questions with confidence. And then from that point, you'll get better at being able to comprehend what you're doing. Start making sense. Okay, so now let's go to the handout which I gave you. And we'll talk a little bit about these 6 examples. And we'll work through these one at a time, really focusing carefully on the words here. Kind of like, here's the word velocity, here's the word speed, here's the word acceleration. Here's the word displacement and the word average velocity. You got to be careful. There's the displacement and the average velocity. Being very careful you follow that. Here's the word total distance. Okay, you see these words, but you got to make certain you understand what they're asking, that you get it straight, that you know what to do before you start answering the question. So what I'm going to do is pause this recording, let you guys take a quick break, and then we'll come back and jump into this. So on this handout, our first question right here. First question is exactly is on page 128 of your textbook. It says a heavy ball, not just any ball, but a heavy ball, okay, is released from rest at time 0 seconds. The equation of its free fall is S equaling 4.9 t squared. How many meters does the ball fall in the first 2 seconds? So the first question is how far does it fall? Well, S is the distance the heavy ball is moving. And I like to write this stuff in function notation. So part A is how far does it fall in 2 seconds, which would just be to put 2 seconds into your distance formula, which makes this a 4.9 times 2 squared, which Thank you. 19.6 meters. There's the word meters right there. So it fell 19.6 meters in the first 2 seconds. Then part B says, what is its velocity, speed, and acceleration? Velocity is your first derivative. Speed is almost the same thing as velocity, but it's the absolute value of velocity, and the acceleration will be your second derivative. So velocity is the first derivative of your position function. So the first derivative of 4.9t squared is going to be 4.9 times 2, which is 9.8, t to the exponent of 2 minus 1, which is t to the power of 1. So that is your velocity. So then it says, what is your velocity at 2 seconds? So S prime, let's change that. Velocity at 2 seconds is going to be put 9.8 times 2, which is, there you go, 19.6 meters per second. So your velocity, when this object is falling, it's going at 19.6 meters per second after it's been falling for 2 seconds. Now, what is its speed? Well, if your velocity is 19.6 at 2 seconds, your speed at 2 seconds is just the absolute value of 19.6, which is still 19.6. There will be times where, of course, your velocity will be negative, and so speed will be to make it positive. Then the next question is acceleration. Well, acceleration is the derivative of velocity, or the second derivative of your position function. So if velocity is 9.8t, the derivative of velocity will just be 9.8. So your acceleration is 9.8 meters per second squared. So you have constant acceleration, which is that gravitational tug is what it is. Okay. There you go. Yeah. So that's not bad. And did I tell you all about going skydiving?
You said something about it.
Yeah. Well, when you go skydiving, if anybody makes such a big deal out of it, it's really not that big a deal. When you first jump or fall out of the plane or whatever, it's that instant, it does kind of just take your breath away, but it doesn't take, just like seconds before you level out at a constant speed. And then you're falling, I think they said like 120 miles per hour or something. You're just falling, but it's a constant rate. So there's no thrill anymore, It's just, okay, I'm falling. The wind is in my face like crazy. Okay, whatever. And then finally, the chute's pulled. And when you pull the chute, then you start getting that feeling again of, okay, this is fun again, because you can kind of whip it around and play with your speed where you speed up and slow down. And that's where you got that feeling of acceleration where it's kind of changing, jerking you, okay, where it becomes more of the thrill. But you do level off and you fall at a constant rate, and there's no sensation really in it. It's just beautiful.
But a video of some guys base jumping, and one of them says that it's like a dream, like you just suspended.
Right. It's like you're suspended with just lots of wind in your face.
Until, like, you get to a certain point, and you pull your chute, and you wake up. It's just
Yeah, it's like, woohoo! Here we are.
How high up did they drop you? Like 30,000 feet?
How high were we? I can't remember. I think it was like 13,000 feet. Yeah. It was pretty cool.
That's probably where I'd start.
Okay.
Up to things which aren't actually as high, but
So let's go on to the next example, which is straight from your textbook. A dynamite blast blows a heavy rock. Everything is heavy around in this book, okay? A dynamite blast blows a heavy rock straight up with a launch velocity of 160 feet per second. So it shoots it at 160 feet per second. It reaches a height of, and this is your height. This is what's determining your height. This position function, this S, that's determining your height. This feet after t seconds. How high does the rock go? In other words, when does the rock peak out before it starts to fall? Okay? So in other words, if you want to know when the rock reaches its highest points, at that split second it stops, right? And then it changes direction. So to get the highest point is to define when the velocity is 0. Okay, so we've got to figure out the velocity. So our goal is to figure out where the velocity is 0, which means that that rock changed directions. It stopped for just a split second and then it changed directions. So here's your position function, your height of this rock as it's moving very quickly after having been launched by some explosion. And so now you're going to come up with your velocity, which is the first derivative of that position, which is 160 minus 32t. Now when that rock reaches its peak location and turns around and starts to fall, that's where this velocity equals 0. So we set this velocity equal to 0 to find the time that rock was in the air before it stopped and turned around to come back down. So set it equal to 0. So now if I set it equal to 0, I get 160 equaling 32t. I divide both sides by 32, and I get 5. So that means that at time equaling 5 seconds, the velocity of this rock equaled 0, which means it peaked out and it's going to fall. All right, so what was the question again? This didn't answer the question. How high does the rock go? How high, what is its peak before it finally starts falling? Well, the height, remember, the height is this s function. So the height is this s of t, and the time it took to reach its maximum height was 5 seconds. So you're going to calculate s of 5. How high is it at 5 seconds when it's going to turn around and start falling? So this is the 160 function, 160 times 5 minus 16 times 5 squared. Did you get 400 feet?
400 feet, yeah.
Okay, so it shot it up 400 feet, so it took off really fast. It kind of gradually slowed down until it stopped at 5 seconds, and then it's going to fall. So that's how high it went. Yeah, it's up there for a heavy rock. Not any rock, okay? Okay. What are the velocity and speed of the rock when it is 256 feet above the ground on the way up, and then again on the way down? What is its velocity and speed? Okay, think about this. It's on the ground. It's going to go up to a height of 400 feet. So it's going to pass the 256 mark until it gets up there at 400 feet. And then when it's coming down, it's going to pass that 256 foot mark again. So that's why it's going to happen twice. So in other words, I wonder when the height is equal to 256 feet. When is the height? What is the time? How many seconds does it take for it to first hit that height and then to fall at that height? So let's see. The height, which is this s of t, when does it equal 256? Well, it does when 160t minus 16t squared equals that 256. Now, this is a second degree function. This is like a parabola right here. So this is, I'm going to reorder this and make it a negative 16t squared plus 160t. You got to set this thing equal to 0 to solve it, right? So you're hoping it factors. If it doesn't factor, how would you figure this? The quadratic formula. Okay, so I'm going to take out a negative 16, and when I do, I get a t squared minus 10t, and this happens 16 times. So this is a negative 16. This is what a t, 8 and 2, minus 8, minus 2. So we get a t equaling 8 and a t equaling 2. So those are the two times. So at 2 seconds, after it's been launched, 2 seconds, it hits that 256 height. Then it goes up at 400 feet, it turns around, it comes back down, and at 8 seconds, it hits it again. So at 2 seconds and 8 seconds are the times that it's going to get to 256 feet. So what is the question? What is the velocity and speed of the rock? Okay, so we want to know the velocity at 2 seconds, and we want to know the velocity at 8 seconds. So go to your velocity. We're in the world of velocity. Here it is up here. Okay, velocity is right here. Go up there, that 160 minus 32t. So this is 160 minus 32 times 2, which is 160 minus 64, right? Which is that right? 160 minus 64, yeah. Which is 96. So it's 96 feet per second on the way up. Yeah, it wants both of them. And then the velocity at 8 seconds is 160 minus 32 times 8, which is going to be a negative number, right? What y'all get? Negative 96. That's interesting. Why is it negative? It's coming down. Okay, so oddly enough, that's pretty interesting. It's going the same speed on the way up as it is down at that time. Oh, and what was the other question here? No. Velocity and speed. So the speed at 2 seconds is the absolute value of 96, which is still 96. And the speed at 8 seconds is the absolute value of a negative 96, which is 96. And what is this, meters? Feet. These are both feet per second. Okay, part C. Hope I don't have a whole lot to do because I'm running out of space. What is the acceleration of the rock at any time during its flight? Well, that's an interesting question. Let's just figure out what acceleration is. Okay, acceleration is the first derivative of velocity, the slope of the velocity line. Okay, where's velocity? Up here in the square. There's velocity. Okay, so the first derivative of velocity, the first derivative of 160 is 0, and the derivative of a negative 32t is a negative 32. So velocity is a negative 32. Okay, a negative 32 velocity the whole time. So it says it's staying pretty consistent there. Oh, right, that's acceleration. I'm sorry, that's acceleration, not velocity. This is acceleration. This is a of t. Okay, negative 32 feet per second squared. That makes sense, doesn't it? Now we're making a little more sense. Gravitational pull. Okay, part D. Let me show the question. Right here, when does the rock hit the ground? What do we know about when the rock hits the ground? Do we know how long it takes? Not really. All we got is we got a 5-second thing, a 2-second thing, an 8-second thing, then none of it's on the ground. Can y'all agree that when the sucker hits the ground, the height is going to be 0? Right? When that rock hits the ground, it's going to be 0 feet above the ground. Okay? And height is our position function. So when our position function, 160t minus 16t squared, when that equals 0, that's when the rock makes it back to the ground. Okay? So I'm going to reorder this. I can't stand for it to be written what I consider backwards. Put it in descending order. Let's take out a negative 16t and leave behind a t minus 10. So the negative 16t equals 0 and the t minus 10 equals 0. So we come up with a time of 0 and 10. Does that make sense? 0 seconds says it was initially on the ground, and then it says it took 10 seconds for it to shoot up in the air and come all the way back down and hit again. Pretty straightforward. That's an excellent example just to kind of get you warmed up. Kind of getting the derivatives, getting your notations in there, understanding that the first derivative of the position function is velocity and the derivative of velocity is acceleration. Okay, next question. Here we got to be careful. A little more careful now. Okay. This one's number 3 on page 132. It says, give the position of a body moving along a coordinate line, and kind of what their vision, when they say along a coordinate line, it's like here's some object and it's going to move this way, and then it might move this way, and then it might move this way, but it's kind of staying on a horizontal. So this is where you're going to see displacement and distance, and be very careful when it's moving along a coordinate line. Given a position of a body moving on a coordinate line with s in meters and t in seconds, here it is. S is going to tell you the distance, or the position. Find the body's displacement and its average velocity for the given time interval, which I do not have written here, but it is 0 less than or equal to t less than or equal to 3. So we're looking at a 3-second interval. So it says find its displacement and its average velocity. So it's going to start here and it's going to end somewhere else. So regardless of how many times it goes back and forth before it stops, Displacement is the distance from the point of origin to the point where it finally stopped. Okay? So in part A, displacement, okay, is going to be its S at time 3 seconds. That's the end where it stopped. And the distance at time 0 where it started. Where it stopped minus where it started. Okay? So S of 3 is, oh my, is negative 3 cubed plus 3 times 3 squared. Don't we just love the number 3? Grief. Okay, so it's a negative 27 plus 27 minus 9, which is a negative 9, right? So we started to the left 9 meters. Okay? No, we ended to the left 9 meters, right? We stopped 9 meters to the left. Okay, an initial position would be negative 0 cubed plus 3 times 0 squared minus 3 times 0, which was 0. So we started at point of origin, and no telling us how much we moved around. We ended up to the left 9 units. So to find the displacement, it's where you stopped minus where you started. So it's negative 9 minus 0, and it's negative 9. And displacement can be a negative number. So it would be negative 9 meters, which means really to the left or backwards 9 meters from the point of origination. And it will be negative. So displacement can be negative. Y'all be careful with that. Okay? Then it asks for average velocity. Okay? So the first one we have to do, remember, is its average. So this is not the first derivative. This is not instantaneous velocity as the first derivative. Average velocity is just the slope formula. So we originate at time 0 and we end at time 3. So when x or t is 0, when time is 0, our position is 0. When time is 3, our position is negative 9 or 9 units or 9 meters to the left of the point of origination. So the slope is the negative 9 minus 0 over the 3 minus 0, which is a negative 9 over 3, which is a negative 3. So this is a negative 3 meters per second. So our average velocity, I mean, we averaged kind of to the left direction, 3 meters per second. So that's the first, that's part A. Okay, part B. I guess I could square these off. Okay. Find the body's speed and acceleration at the endpoints of the interval. Okay, the endpoints are where you started and where you stopped, right? Your endpoints are your starting and your stopping. So your first endpoint is where your time equals 0, and your last endpoint is where your time equaled 3 seconds. So if it wants to know speed, then I need to find the absolute value of velocity. So I need to first get velocity and then take the absolute value of it. So here we go. Velocity is the first derivative of your position equation, which is right here, this negative t cubed thing, which I'm having a hard time keeping it all on the screen. Okay, but the first derivative of our position equation is going to be a negative 3t squared plus a 6t minus 3. That's my velocity equation. So now my velocity at 0 seconds will be a negative 3 times 0 squared. Come back, turn blue. Oh, thank you. Negative 3 times 0 squared plus 6 times 0 minus 3, which is a negative 3 meters per second. It's an initial velocity. And then your velocity at 3 seconds is going to be a negative 3 times 3 squared plus 6 times negative 3. Wait. 6 times positive 3, right? Velocity at 3 seconds. Too many 3s. So that's a negative 27 plus 18 minus 3. Is that 6? Okay. So the speed when time equals 0, in other words, when you first take off, is the absolute value of negative 3, which is 3 meters per second. They must have launched this thing. And then the speed at time equaling 3 is the absolute value of 6, which is 6 meters per second. Okay. Boy, they ask a lot of questions. Find the body's speed and acceleration at these endpoints. Okay, so what is acceleration? Well, acceleration is the first derivative of velocity. And here's my velocity. You've got to find it somewhere in all of your work. The first derivative of velocity is a negative 6t plus 6 minus 0. So your acceleration at time 0 is a negative 6 times 0 plus 6, which is 6 meters per second squared. And your acceleration at 3 seconds would be a negative 6 times 3 squared. I'm using the, hold on, no I'm not, this one. I got to get these right. It's a negative 6 times 3 plus 6, which is a negative 18, plus 6, which is a negative 12 meters per second squared. Was I on the monitor? Y'all gotta holler if I'm not on the monitor. You can't see it. Okay, then we have another question. I'm not going to have a whole lot of room here. And this one might be a difficult one for you to, I don't know, you'll not catch it easy enough. When, if ever, during the interval, during this time interval, does the body change direction? When, if ever, does the body change direction? Okay, so let's think about this. Does it change direction? Okay, for it to change direction, it has to stop. It has to stop. So we need to know when the velocity equals 0, which means this object stopped. Now, if velocity doesn't change sign, if it doesn't go from negative to positive or positive to negative, it doesn't change direction. So velocity also has to change sign. It has to be going forward and then backward, or backward and then forward. So velocity must change signs when it stops. So for it to change direction means that velocity must change signs when it stops, okay? So we got to get the sign. Is it positive? Is it negative? Is it negative and negative? What is going on here? Okay, so the first thing we do is we figure out where does the velocity equal 0? Where is it stopping? Okay, well, our velocity was a negative 3t squared plus 6t minus 3. That's our velocity. And we want to set it equal to 0 to figure out at what time, how many seconds were we in when it stopped. Okay, so this is a quadratic function. I'm hoping it will factor for me. Take out a negative 3, it will leave behind a t squared minus 2t plus 1. This is nice. This is a t minus 1 times a t minus 1. So when t minus 1 equals 0, time is 1 second. So at 1 second, this thing stopped. But I don't know what it did. Did it back up or did it continue in the same direction? But we know that the object stopped at 1 second. Now, to determine if it changes signs, we need what we call a sign graph. And it's probably been a while since y'all made a sign graph. But to determine if it changes signs, I'm going to create a sign graph. And I guess we did this in inequalities. Okay, so we got a time equaling 0 to 3. And we know that at 1 second, it stops. So right here, it stops. Velocity, that's a 1. Okay, so velocity. So now, between 0 and 1, is velocity negative or positive? We'll go up here to your velocity. Let's pick a checkpoint. Maybe we'll pick at 0.5. So let me see. Velocity at 0.5, is it positive or negative? It would be a negative 3 times a 0.5 squared plus a 6 times a 0.5 minus a 3. And I'd have to put that into the calculator. And I show it's negative, isn't that right? It's negative. Okay, so it's negative. It's going backwards between 0 and 1 seconds. It's launching it backwards. Okay, so let's pick another test point between 1 and 3. Suppose we pick 2. What is the velocity at 2 seconds? Well, this is a negative 3 times 2 squared plus 6 times 2 minus 3, which is a negative 3 times 4, which is a negative 12, plus 12 minus 3, that's negative again, right? So it remains negative. So it was going in the leftward direction, it stopped, and then it kept going leftward. So it did not reverse direction. Okay? Always left, or backwards. Backward, stop, continued backward. So, no, it did not change directions. Okay, it did not change directions. It stopped, but it did not change directions. That's a really nice question. Okay, let's look at the next one. Four, at time t, the position of a body moving along the x-axis is that. Find the body's acceleration each time the velocity is 0. So we're going to have to calculate the second derivative. We have to calculate the first derivative, set it equal to 0 to get time, and then acceleration at that point. Find the speed each time the acceleration is 0, and then find the total distance traveled by the body from time equal to 0 to time 2. These are 3 very different questions. Okay, and the last one's the most interesting one, because this is distance, not displacement. Okay, so if we're going to come up with acceleration, we're going to have to get to the second derivative. And if we want to know where the velocity equals 0, we've got to have this first derivative set equal to 0. Okay, so here's our position equation, which is really, in this case, distance from point of origination. Then we're going to get velocity, which is the first derivative, which is 3t squared minus 12t plus 9. And we're also going to want to know acceleration, which is the first derivative of velocity, which is 6t minus 12, using all those differentiation rules. And when you do your homework, you'll get quick at that. Okay, so we got all of our formulas there. Now let's answer some questions. Part A. Find the body's acceleration each time the velocity is 0. Okay, we got to figure out when the velocity is 0. So velocity equals 0 when we set 3t squared minus 12t plus 9 equal to 0. All right, so hopefully this will factor. If not, we'll have to go to the quadratic formula. Very good. I get time equaling 1 and time equaling 3. So this object stopped at 1 second and at 3 seconds. So now we know when it stops. But the question really is, find the body's acceleration when the velocity is 0. So, really, we want to know acceleration at 1 and acceleration at 3. So go up to our acceleration formula, which is 6t minus 12, which would be 6 times 1 minus 12, which is a negative 6. And at 3, it'll be 6 times 3 minus 12, which is 18 minus 12, which is positive 6. So those are my accelerations. Those are in, it doesn't say, meters. There it is, meters. I guess we assume meters per second. All right, that's part A. Part B says, find the body's speed each time the acceleration is 0. Okay, that means the speed is constant. If there's no acceleration, your speed is constant. Okay, so find the body's speed when the acceleration is 0. So we got to figure out when the acceleration equals 0, which means when does 0 equal to 6t minus 12? Well, this occurs when t is 2. So at 2 seconds, the acceleration equals 0. So the speed at 2 seconds means find the absolute value of velocity. So the goal is to find the velocity at 2 seconds and then take the absolute value of it. The velocity at 2 seconds, go back up to the velocity formula. This becomes a 3 times 2 squared minus a 12 times 2 plus 9, which is 3 times 4, which is 12, and 12 minus 24 is a negative 12, plus 3 is a negative 3. So speed at 2 seconds is the absolute value of negative 3, which is 3 meters, right? Per second. Meters, yes. So the speed is 3 meters per second when the acceleration is 0, which means it's holding steady. Holding a steady, constant rate of speed. Okay, now this part C is going to take a little space. Find the total distance traveled by the body from time t equaling 0 to time t equaling 2. Now, you got to figure out if the crazy object stopped anywhere in that time period and if it changed direction. And then you got to calculate the distance of all that. So we do know that by the velocity in part A, that at time 1 and at time 3, the thing stopped. But we don't know if it reversed direction or not. So we can calculate all the distance that it covered. But what we do know is we know that the object stopped at time equaling 1 second. Well, it stopped at 3 also, but we don't care because we're only looking at the time from 0 to 2 seconds. So now the question is, did it change direction? At 1 second. Before we can calculate the distance covered, not displacement, but the whole distance. So we're going to have another sign chart. So here comes your sign chart. Here's velocity. You're going from 0 to 2 seconds because the question said only during 0 to 2 seconds, give me the distance it covered. So we're finding velocity from 0 to 2 seconds. We know at 1 second this thing stopped. All right, let's look at the velocity to the left. It's say 0.5. So what is the velocity at 0.5? Is it negative or is it positive? Well, this is 3 times 0.5 squared minus 12 times 0.5 plus 9. Is it negative or positive? I show it to be positive. Okay, so it's going in a forward motion. Okay, let's pick something between 1 and 2. Suppose that we pick 1.5. The velocity at 1.5 is 3 times 1.5 squared minus 12 times 1.5 plus 9. And when you calculate that, it's negative, right? So we did get a change in direction. It was going forward, then it stopped, and it went backward. So we have to calculate the direction of both. Or not the direction, the distance in both cases. I need a piece of clean paper. All right, so now we know what we need to do. We need to know the distance covered when from between time equaling 0 to time equaling 1, and we need to add it to the distance between time equaling 1 to time equaling 2. Okay, the distance from time equaling 0 to time equaling 1, what was your original distance? Okay, your distance or your location, your position function is t cubed minus 6t squared plus 9t. So you originate when time is 0, and 0 cubed minus 6 times 0 squared plus 9 times 0 is 0. And then how far did you get 1 second later? This is 1 cubed minus 6 times 1 squared plus 9 times 1, which is 1 minus 6 plus 9, which is 4, right? So the distance in the first second is 4 minus 0, which is 4 meters. Now the second part is what was the distance covered from time equaling 1 to time equaling 2, because you stopped and you went the other way. So the time at 1 was 4, or the distance, you were sitting 4 units out at 1 second, and at 2 seconds, it's 2 cubed minus 6 times 2 squared plus 9 times 2, which is 8 minus 24, which is negative 16 plus 18, which equals 2. So what's the distance between 4 and 2? 2. So total distance traveled would be 4 meters plus 2 meters, which is 6 meters. That's probably your hardest question, because you're going to have to start off by determining if this object changes direction or not. And then you jump in there and you have to go through all this computation to get the distance going backwards as well as the distance going forward, which is not the same thing as displacement. Had you figured displacement, what would you have come up with? 2. Because you started at 0 and you ended at 2. So displacement was only 2 meters, but you really covered a total of 6 meters. All right. I'm moving along. I know y'all are getting tired. Is it getting late? We're close. Okay. This one's pretty easy. Marginal cost. This is the stuff I don't like. This is like economics. One of you guys is good at this. Taking an economy class, economics class, or okay, the marginal cost of production is the rate of change of cost with respect to the level of production. Something like DC dx, DC, C being cost, and X being the number of items you're producing. Example, suppose it costs C of X, X cubed minus 6X squared plus 15X dollars. So you're going to put a number in there and it's going to give you a dollar figure to produce X radiators. So you put the number of radiators into this and it tells you how much it's going to cost you to make that many radiators when you're making between 8 and 30 radiators. So it varies. If you're making 50 radiators, it's a different equation to determine cost. But if you're sitting in the range between 8 and 30, this equation is going to tell you how much it's costing you to make those radiators. And the dollar revenue from selling the radiators, this is the money that's coming in. The revenue from selling the radiators is this formula. So the cost to make them and the revenue when you sell them. Your shop currently produces 10 radiators a day. That doesn't seem like a lot. Maybe that's good. I don't know. Come on. Hey. Your shop produces 10 radiators a day. About how much extra will it cost to produce one more radiator a day? Okay. The cost of producing one more radiator a day when 10 are produced is approximated by the first derivative of the function. So to find the variation in the increase of one more, okay, which is like the slope of that function, is to take the first derivative of the cost function at the point that you produce 10. So C of x equals x cubed minus 6x squared plus 15x. C prime of x is 3x squared minus 12x plus 15. That tells you kind of like the cost per unit, the slope of the line, the cost per unit, cost per radiator kind of thing. So if you're looking at the cost right after producing 10 radiators, the rate of cost as you're doing this, you're going to put 3 times 10 squared minus 12 times 10 plus 15. How much y'all get? 3 times 100 minus 120? Is it 195? That's what I have in my notes. Yeah, I think it's $195. So to make one more radiator, it's going to cost them $195. That's your materials and your labor and the electricity for the air conditioning. I don't know what it is, but it costs them money to make radiators, and that's about how much it would cost them to make one more. Okay? So then it says that would be the extra cost of producing one more radiator. To produce the 11th radiator. That's what it is at the time when you just finished the 10th one, kind of what's going on to make it, it's kind of hard to explain it, but yeah. And it's got to be different per unit you make. I don't know, maybe the factor is how tired is the person at this point. Takes them a little bit longer to do their job, you know, or maybe some of the equipment is hot and it's not running as quickly or faster or whatever. Okay, so then it says, what is your estimated increase in revenue? Okay, revenue, you have the second function. Revenue is the money coming in when you sell them, more or less, with a lot of factors involved in it. So how much is the revenue going to vary if you go a one more 11th radiator? So this first derivative, revenue change in revenue, is 3x squared minus 6x plus 12. So your change in revenue when you reduce that, right after you produce the 10th one, you're going into the 11th one, is 3 times 10 squared minus 6 times 10 plus 12, which, thank you, is $252. So they're going to make $252 more, and their cost is only $195. So they're going to have more revenue. They're still going to get a profit, in other words, if they produce an 11th one. They'll still get a profit. But there's other factors that are involved in here. You know, your laborers are tired. Are they going to stay? Are you paying overtime to produce that one? You know, all these factors are in here. So this is kind of what helps people project what they should do in order to make certain that they're coming up with the most profit. Revenue.
In this case,
Increase in revenue.
how can you define it as the first derivative? Like, what was the thinking?
The change in cost per time, per unit, it's going to cost them cost per unit. Cost per unit. So this is like cost per one radiator. But the cost it takes to produce the third radiator might be a little different than the cost to produce the 11th or the 10th. That's kind of hard to, even for me to we want it to be straight and easy, but it's not that easy. Okay? So the cost to produce one more radiator, I should say. One more kind of radiator. Cost. I know this is the economy business. Makes it a little harder. This is, it's not necessarily the cost, it's the change in the revenue when you produce one more. It's the increase in the revenue. Is it an increase? Yeah. The increase in the revenue, the amount of increase in the revenue when producing one more, specifically the 11th one, radiator. It won't get any harder than that. They're pretty careful. Okay, and then finally the easy one. Thank goodness, because we are so close to being completely out of time. I know we are. Hurry. Okay, here we go. They get easier as you go. Okay, the area of a circle is related to its diameter by this following equation. So, of course, as the area increases, the diameter is going to increase of your circle. How fast does the area change with respect to the diameter when the diameter is 10 meters? So I always visualize like water and a droplet of water hitting a pool of just perfectly still water. And you can see the concentric circles as it expands, right? Your droplet makes a bunch of concentric circles on the lake or pool or whatever. And so as that circle is getting bigger, the diameter is getting bigger, and so is the area of the circle. So they're saying if you could freeze time or take a picture at the instant the diameter was 10 meters, and remember it's changing, but if you could stop time at the point where the diameter is 10 meters, what is the area of that circle? That's what the question is. So area is pi fourths times diameter squared. So you want the rate of change because it's changing. So we're going to take the derivative of area. Y'all might not like the way this looks. With respect to d. You know, if this had said y equaled pi fourths x squared, right? Then you would say dy dx because it's y written in terms of the x variable, which is y prime. And this would be 2 times pi fourths, which is 2 pi fourths x, which is pi halves x. But over here, you don't have that. You have this a business equaling pi fourths d squared. So oddly enough, you're doing dA dd, which would be a prime, which would be 2 times the pi fourths, d to the exponent decreased by 1. So it is pi halves d. D is diameter. I don't like d. Whatever. Okay? So, the change in area, A prime, equals the change in area of the circle. And so A prime, when the diameter is 10, is pi halves times 10, which is 5 pi, which is 15 point. Yeah. Which would be what? Meters squared? What would that be?
I put meters over 1 because they don't really give you a unit.
Meters per time.
Meters
Yeah, it is time.
change in meters.
That's the answer, okay. You have a wonderful time doing your lovely homework. Doesn't that just make you happy? And I'll see you on Wednesday.